Okay, so let's look at section 8.3, which is going to be margin of error. And this is error as it relates to our confidence intervals, okay? So keep that in mind. So, introducing margin of error. The civilian labor force. Now, if you remember, we did the civilian labor force problem in the one mean z interval procedure in the last video. So if you've forgotten about that, go back and watch video from 8.2. We did this particular problem. Now, before we get started with the actual problem, let's recall a few things from that particular problem. We learned that the confidence interval was represented by this formula here, times our standard deviation over the square root of n to the sample mean plus z sub alpha divided by 2 times the standard deviation divided by the square root of n. That's what we learned last time. And we also learned that our standard deviation for that problem was 36.4. And once we figured out what this equaled, it equaled 3.4. Okay, and so we had 36.4 plus 3.4. And so last time we figured out that our confidence interval was 33.0 to 39.8. And that was our confidence interval. And we said that what this meant was that we were 95% confident that the mean age was between 33 and 39.8. Okay, if you remember from the last problem. Now, let's look at letter A. Discuss the precision with which X bar estimates U. Alright, so remember what we said about precision. The larger the larger the confidence interval, the wider the confidence interval, the less precise it was. So our confidence interval here, because it's a 95% confidence interval, the precision is very, very minimal. So remember what we said. We said that decreasing the confidence level increases the precision. So a 95% confidence level would be a very poor in terms of precise because our interval is wider. So essentially what we have, if we look closely, what quantity determines the precision? Well, if we look closely, this is what we actually have. You have X bar, you have X bar minus Z sub alpha divided by 2 times the standard deviation over the square root of n, and you have X bar plus Z sub alpha divided by 2 times the standard deviation over the square root of n. Okay, this is our confidence interval. So in this case, it's 33.0 to 39.8, and 36.4 is in the middle. Now, why is that important? What quantity determines the precision? That's the question we're asking. Well, look right here. This area right in here is 3.4. This area right in here is 3.4. We get that from here and from here. These two green areas here represent the quantity that determines precision. Now, what quantity is this? This particular quantity is Z sub alpha divided by 2 times the standard deviation over the square root of n. That is the quantity that is determining our precision. And now we have a special name for this. We call this the error. This is the error in our in our sample mean. essentially is what this is doing. This is the error that we have in our sample mean. So if you look at letter C here, in section 8, as we saw in section 8.2, we can decrease the length of the confidence interval and thereby improve precision of the estimate by decreasing the confidence level from 95% to some lower level. Now, suppose, however, that we want to retain the same confidence level but still improve precision. How can we do that? Well, the key is the error here. In order to improve precision, we have to reduce our error. Does that make sense? In order to improve precision, we need to reduce our error. Well, how can we reduce error in this problem? Well, you can't do anything to z sub alpha divided by 2. You can't really do anything to the standard deviation because that's determined by the sample or the population. But what we can do, our n right here, if we increase the sample size, it will in turn reduce our error because we'll be multiplying by a smaller and smaller fraction right here the more we increase the sample size. And so because of that, it will reduce our error more and more. So increasing sample size will reduce your error. And I'm sure, like it says in letter D, I'm sure that's what I just explained to you. I'm sure that makes sense, that if you increase that sample size, you'll reduce your error. Now, we actually call this error the margin of error. And so the way you need to think about all of these is the way I had it drawn before. You need to think about all of this. You need to think about this is your x bar. This is your x bar minus your error. This is your x bar plus your error. And so essentially what you have here is this piece in here is your error, and this piece in here is going to be your error. Okay? That is what we mean by margin of error. Okay? So, and I've already said this, but we'll go over it again. The length of a confidence interval for a population mean, and therefore the precision with which the sample mean estimates the population mean, is determined by the margin of error. For a fixed confidence level, increasing the sample size improves error, and vice versa. Increasing the sample size improves precision, and vice versa. Okay, so that's what I said earlier. Now, suppose I want to determine the sample size from the error. Well, here's the formula to do that. Now, I want you to get what this is, folks. Don't overthink this, okay, please. This formula that they have given you is basically this formula here solved for n. So if you solve this formula for n, we would get E equals z sub alpha divided by 2 times the standard deviation over the square root of n. And you can cross multiply here. And so you would get E times the square root of n equals this. Then divide by E. And so the square root of n equals z sub alpha divided by 2 times the standard deviation divided by E. And to solve for n, we square both sides. So see, that is this formula right here. So if we know our standard deviation, if we know, or if we can find by using the confidence level, if we can find our z sub alpha divided by 2, and if we know the error, we can very easily figure out what our sample size needs to be for a certain specified margin of error. Okay, so for instance, same problem again, okay, with the civilian labor force. So determine the sample size needed in order to be 95% confident that the mean is within 0.5 year of the estimate, x bar. Recall that the standard deviation is 12.1. So remember, to solve for our sample size, which is determine the sample size, is what we're trying to do. Remember, it's z sub alpha divided by 2 times our standard deviation over e squared. Now, we've already solved it. This goes back to that same problem. Z sub alpha divided by 2, if you go back and look at our last video, was 1.96. Okay, if you got your book, you can flip back and look at that as well. But it was 1.96. So you already know what that is for the 95% confidence level. That's what we solved for last time. So I'm not going to solve for it again in this video. Feel free to go back and watch section 8.2 video. You can see me solve for it again. But that is all we've already previously solved for that information. So I'm going to go ahead and plug that in. My standard deviation is 12.1. And my error here is 0.5. Within 0.5, that's my error. Okay? So square this. And when you do that, you should get 2249.79. Now, don't leave it like this, unless it asks you to in MyLabs Plus. Don't leave it like that, because we're trying to determine sample size. Really, you can't have 0.79 of a sample, so I would round that up to 2250, so that you could have 2250 would be a better estimate, because you can't have that part of a person, so to speak. So 2250. Okay, so that would be letter A. Now, letter B says, find a 95% confidence interval. Now, we're finding the interval, okay? Finding the interval, which is x bar plus the error x bar minus the error to x bar plus the error. That is our interval, remember. Okay, so find a 95% confidence interval for a population mean if a sample of the size determined in Part A has a mean of 38.8. So the sample has a mean of 38.8. So here's our sample. Here's our interval with the sample. Now, in Part A, they told us the error. The error is 0.5. That was given in Part A. This has to do with Part A. So, we take this problem and we can find out what this interval is simply by taking our error and substituting it in. So our confidence interval is going to be 38.3 to 39.3. So, here's what I want you to notice. We increase the sample size here. Same problem we've been working with. If you remember the original 95% confidence interval, the confidence interval was 33.0 to 39.8. This was our original confidence interval, and we were 95% confident that it was in this interval. But we said it wasn't very precise because it was a large confidence level like that. Well, if we want to keep the confidence level the same, but we want to increase our precision, we needed to increase the sample size. And that's what we did in part A. We increased the sample size, we decreased the error by doing that, because remember, our error was 3.4. So we decreased the error and increased our sample size and still have the same confidence level, but look how much we increased our precision. Look at this. Look how tight that interval is compared to this one. This one's much smaller because we increased our sample size, but we still have a 95% confidence level. So keep that in mind. To improve the precision of the estimate, we need to decrease the margin of error, which means increasing the sample size, because the confidence interval, when it has a wide range for possible values, the precision is poor. So that 95%, had a wider range, so it was a poor confidence level. Now, I'm going to be honest with you folks. In real world instances, depending on your sample size now, keep that in mind, an error of 3.4 like this one had is probably not going to be very big if you have a large sample size. Okay? But we only had a sample size of 50 in the beginning. So an error of 3.4 ended up being a large error, a poor precision. That's why it gave us poor precision. The smaller error gave us more precision in a lesser interval. So what I want you to realize is whether this is poor, how do you know whether that length of that interval is poor or not? Well, a lot of it has to do with the size of your sample, and a lot of it has to do with the size of your sample. Matter of fact, everything of it has to do with your size of your sample, and using a little common sense to say that wouldn't be too bad with that size sample. Okay, so keep that in mind. Keep that in mind as you are working through this. Okay, remember our rule from section 8.2. Decreasing the confidence level improves the precision. So keep that in mind, that long confidence intervals indicate poor precision. Short confidence intervals indicate good precision. So keep that in mind, that the shorter it is, the better. And you wouldn't call this, because 3.4, you wouldn't call this terrible precision, but it's not as good a precision as 0.5. 0.5 is very good precision. Now, when you start getting into different facets of life, 0.5 can mean life and death. So you might want it 0.00005. So it really depends on the situation you're looking at as well. Especially if you're a nursing major and you're trying to do an average dose, you want to be as close to that average as possible. You don't want to have a large error and not give somebody enough or give somebody too much, things like that. Okay, so keep that in mind. Some real life applications with that. Be able to solve for your sample size, like we did here, be able to find the error. All right, I hope this made sense to you. Have a great day.